All right, so let's suppose that being the Hershey's chocolate freak that I am, I eat 3 candy kisses today, I eat 12 the next day, I eat 48 the next day, and so on. All right, so that's the sequence of numbers we're talking about. So let me ask some questions about this. How many will I eat on the 8th day? All right, so that's the first question. How many will I eat on the 8th day? All right, so what's your thought on that? It's the second formula, and the reason it's the second formula is because what's going on here? We're multiplying by 4, and when we multiply by the same number over and over and over again, what kind of sequence is that? Geometric. And the number that we multiply by, the 4, is called the common ratio. So obviously, if it's geometric, it's going to have a ratio, so it's going to be one of these formulas that's got an R in it. And since we are asking for the 8th number in the list, right? We're not going to add them up. Sometimes we do, but not now. We want the 8th number in the list. That will be the formula Jason pointed out. So the 8th term is 3 times 4 to the 7th. So we would just figure out what that is. 49,152 candy kisses on that day. All right, geometric sequences grow really, really fast. We talked about that, I think. All right, so let's ask another question. So that's one possible question that could be asked. Another question is, how many will I have eaten in 14 days? Now that's a different question. Does everybody see that? That's a different question. Will I have eaten? What does that imply? All of them. All the total number of candy kisses I've eaten. So which formula is that going to be? This one right here? This one. Because this sequence is what kind? Geometric. And I'm summing it up. So here we go. The sum of 14 terms will be the first term minus the first term times the ratio to the 14th over 1 minus the ratio. Now when you type these in, type them in any way you want, but I type it in doing the numerator, and then I hit equals divided by -3. Oh gosh. I think it's 268,435,455. I think I got all the numbers in there. In 14 days.
When do you use that last?
We'll get to that in a minute. Okay? Now, one more question that could be asked given the same scenario. A third question that could be asked is, on what day will I eat 777,777 kisses? All right? So what's that look like? What's that setup going to be? On what day will I eat that many?
So it'd be the second one.
It'd be the second formula again, because what is that number? What is that? Isn't that just going to be a number here eventually in this list? Am I adding up to get that? No, that's a number in the list, so I'm going to use this formula. Well, how's that going to look? How do I apply that formula?
So you do
777,777 equals 3 times 4 to the n minus first. Right?
How'd you know that was geometric? It's the same problem.
Same sequence. All right, how do I solve that?
Oh, divide by
You gotta divide by 3 first. You're gonna have this divided by 3. Oh boy.
Could you have to do logs?
You have to do logarithms,
Oh, yeah.
that's exactly right. We're gonna use logarithms.
So then,
Yep, those of you that forgot or thought you could forget all that, oh no, no,
So
no.
it would be log 7.
So the log of this guy equals, remember when you take the log, you can pull the exponent off? That's why we do it.
And add 1.
Well, first we'll divide by that. So we'll have the log of this big, huge number over the log of 4 equal to n minus 1. Then we'll add the 1, Brenton, after we get that figured out. So I need to do the log of my numerator divided by the log of my denominator, and then I'll add 1 to it. It actually came a lot closer than I thought it might, but tell me about that answer. What does N stand for? Go back to the very beginning. What was this 3 here? That was first term, right? And it represented what?
The number of times.
The number of candy kisses I ate on the first day. And then here N was 2. It was the number I ate on the second day.
So it was N2. Or like, no, I meant days.
So what does that mean?
Almost the 10th.
It's almost the 10th term, but it's not the 10th term, right? So this question says, on what day? We got to be careful. It would be in between the 9th and the 10th day, but in terms of a sequence, we really want this number to be what? A whole number. So if the question had been, which term is 7777? The answer is it's not. Does everybody see that? That is not a term of this sequence. If you wrote this sequence out, you would never see this number. Now, in terms of this particular question that I asked, at some point, will I eat that many? Well, it would be sometime almost to the 10th day, right? Right before the 10th day started. But the point I really want to make is, if the question said, which term is that number? The answer would be, it's not. Because this needs to be a whole number in order for it to be an actual term of the sequence. Do you see that? You need that to be a whole number. All right. Now, did we talk about last time we were together? All right, so that's what your quiz is, that's what half your quiz is going to be over. That kind of thing where I give you some scenario and you're going to use one of these formulas to answer the question. Okay? And we practiced some from our packet the other day. Did we talk about sigma the other day? Sigma. We didn't talk about that? Okay, so we need to talk about that right now. Sigma. Look in your packet on page 3 or 4. Page 4. Look on page 4. And question number 2 looks like this. This squiggly line is a sigma. You have probably seen a sigma before. Has anybody ever seen this symbol before? Where?
Physics.
You used it in physics.
Yeah, I took on it.
What did you use it in physics for?
It was, I forget the exact name of it, but you had to take, you had the bottom term and the top term, and you did something weird with some formula. It was almost, it was between derivatives and something else.
Okay, okay. Anybody else seen it? Mallory?
I saw it in Algebra 2 Semester 2 Summer School online.
Do you remember what it meant?
What I gathered from it was that we put
It means the sum.
And the term that you're using is
Sigma, 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 sigma means sum. So every time you see a sigma, you're going to be using one of your sum formulas. One of your sum formulas every time you see a sigma. If you have used Excel, if you're a person who uses Excel a lot, there is a sigma in the Excel menu, and what that does is it sums the column. That's what it does. You've also seen this on a million college sweatshirts, right? It's one of the letters that's used in a lot of fraternity names and sorority names. All right, so here we go. What does this mean? Well, it means I'm going to add something. I told you every time you see a sigma, you're going to focus in on your sum formulas. But in order to know which formula to use, you need to know which kind of sequence you have, right? So, unless you kind of have an intuition that you trust, you probably want to write out a few of the terms. This is like an abbreviation. It represents the whole series. So here we go. Let n be 1. Whatever this number is, and it's usually 1, but not always. But whatever that number is, you're going to plug it in here. So what do I get? What does this equal if I put in 1? Negative 1. Sigma means sum. So now I'm going to go to the next number, which is 2. I started with 1. Now I'm going to 2. What do I get when I put 2 in? 1. And then I'm going to put 3 in. Put 3 in. And I'm going to put in 4, 5, 6, 7, 8, 9, 10. 10 is the last number I put in. So this tells me I'm adding up all of these, starting with an n value of 1 and ending with an n value of 10. So the last number I would be adding would be 17. Now, I did not write out every term of the sequence. You can if you want, but remember, the only reason I wrote out any of them is because I needed to know if it was arithmetic or geometric, so I knew which formula to use. As soon as I see what's going on, I stop writing them out. You can keep going if you want, but there's really no need to. What is going on here? We're adding 2. If we're adding 2, then it is arithmetic, and we will be using this one. So here we go. How many terms are we adding up? If I had written them all out, how many would there be? 10. Kids, we're going from 1 to 10. That's 10. What's the first one? Negative 1. Oh, what's the last one? Ah, sigma's really nice in this situation because it gives you the first term and it gives you the last term. You don't have to do any fancy stuff. So the answer is 5 times 16, or 80. So that sigma is 80.
This one.
Yeah.
Do you always use the sum on the
Sigma means sum. So I'm going to use some kind of sum. This is arithmetic because of how it's built, added to. All right, let's get down to number 4. Number 4. All right, this is the same exact thing. Sigma means sum, so I just got to figure out what I'm adding up. So here we go. What's the first term I'm adding?
1.
No. Let n be 1. What is the value of the first term that you are adding up? Negative 6. Now we'll let n be 2. Negative 12. We'll let n be 3. Is that enough? I mean, obviously it's going to keep going. Is that enough for you to see what's going on?
Yeah.
What's happening? Multiplying by 2. So that one is geometric. So we'll be using this formula right here. So the sum of 10 terms is the first term, which is negative 6, minus another negative 6 times 2 to the 10th over 1 minus 2. So here we go. Here, let me give you some stuff here. Let's type that in and see what we get. So there's that. And that. That. That's all three. Alright, so what do I get when I type that in? I might notice I got a double negative right here, so I'll get rid of that. Negative 6 plus 6 times 2 to the 10th. I got negative 6138. Did you?
Yeah.
That's it. Now, Brenton is saying, Ms. Ford, what's that last formula used for? Well, that last formula is used for a problem like number 4, or 3, I mean. What's different about number 3? It's a sigma.
You don't know when you stop.
You don't know when to stop. And it isn't that we don't know when to stop, Brenton. It doesn't stop. In other words, this is going to keep going forever and ever and ever. Sometimes you'll actually see an infinity symbol on the top that it indicates this is an infinite series. Now, let's see what kind of series it is. What do we get if we let n be 1? What would that first term be if we let n be 1? 2/3. And if we let n be 2, what's 1/3 squared?
1/3.
No, 1/3 squared.
1/6.
No, 1/3 squared. 1/3 times 1/3. 1/9 times 2. 2/9. Alright, let's do one more. 1/3 cubed.
So 1/27.
1/27 times 2. 2/27. Now we could keep going, and you need to keep going until you figured out what's going on. Is this enough? Can you see what's happening here? What's going on? Well, how are we getting from term to term? What am I'm multiplying by 1/3?
Yeah.
And by 1/3 again. So this is geometric. Now, sigma, sum. This formula is your geometric sum formula, but you can't use it. You can't use it because, see that right there? We don't know what it is, right? I want you to think about, though, what would happen if I did try to use that formula. You don't need to write this down unless you want to, but I want you to think about this. Right, here's my formula. Now I want you to think about, n is going to infinity. That means it's getting really big. So let's think about 1,000. That's not even really big, but let's just use 1,000. Can you describe what happens when you raise 1/3 to the 1,000th power? It's tiny. That's putting it mildly. It gets really, really small. And in fact, if you raised it to the 1,000,000th power, it would get so small that your calculator would say, that's just, I can't deal with that. That's the same as 0.
I got that for 1,000 as well.
1,000, even 1,000. This gets so small, so very, very small, that the calculator just can't deal with it, ignores it. Now, does that actually equal 0? No. But it is I mean, it's so small. So that's tiny. And then you multiply it by 2/3, and then it's even tinier. So all of this is basically 0. So So all that's left is the first term over 1 minus the ratio. This is your formula for an infinite geometric series. Now, the answer to this question then would be really simple. It's the first term over 1 minus the ratio. That's 2/3 over 2/3. That sum is 1. If you started adding up all these numbers and kept going at infinity, it would be 1. In order to do that, the ratio has to have an absolute value less than 1. In other words, the terms of the series need to be getting smaller. If the terms of the series are getting bigger, you can't add them up. They're just getting bigger and bigger and bigger. So infinite series are only summable if the ratio is less than 1. Okay? So that's what we use that formula for. So you have 2 geometric sum formulas. This one is used if you know how many you're adding, like find the sum of the first 10 terms. This is the one you use if you are going to infinity. Okay? Yes, gotta be geometric. See the R? R stands for ratio. Gotta be geometric. All right, so that takes care of that. All right, now we have one more thing to talk about. So there aren't going to be any sigmas on this quiz that we're taking tomorrow. There'll be sigmas on your quest. When you see a sigma symbol, what do you automatically think? Sum. The first thing then you got to figure out is, what am I summing? Is it arithmetic or geometric? Because that's going to determine which formula you use, right? And how do you tell whether it's arithmetic or geometric? You just write out a first fuse. So if the sigma is structured like this, you're going to plug 1 in, and then you're going to plug 2 in, and then you're going to plug 3 in, and you're going to keep plugging until you got enough terms there to figure out whether it's arithmetic or geometric.
If there's nothing on top of the sigma, can you just infer that it's going to be geometric?
No, because what if I ask you to sum an infinite arithmetic one? You can't do it. You would have to say no answer. So no, you can't just assume. You need to work it out every time. Okay? Now, some of you, after you practice a couple of these, are going to be able to look at it and say, oh, that's going to be arithmetic. Or that's going to be geometric. But you have to know that before you start the problem. So you figure it out one way or the other. Okay? Now, the next thing we're going to talk about, and it really ties in with this conversation we just had about those terms getting smaller and smaller and smaller, we're going to talk about limits. And we're going to start with, actually, let me start with one that's a little easier than that. So I can't remember if I used this notation earlier in the year. This means the limit as n approaches infinity. Did I use that notation before? I think we did with n behavior. So we're kind of like doing n behavior, but we're only doing it with, right now, with things that look like this. So, and it ties in perfectly. Anybody remember back when we were talking about n behavior, what did we use the limits for? Do you remember there was a piece of your graph that you needed limits for? Does anybody happen to remember what that? Which asymptotes? The horizontal ones. This is how we found our horizontal asymptotes. We're almost done here. Those of you that are yawning.
Or are these just problems that you're in?
These are just problems. Yep, we're gonna go through these. We don't need these anymore, so I'm gonna erase these. All of these problems are exactly the same kind of problem. They'll have different answers, but they're exactly the same kind. We're gonna look at, because I'm out of time, so I'm shortening everything. We're only gonna evaluate 3 kinds of limits, okay? And one of the kinds of limits we're gonna do are these problems where we have n's over n's. You see how all of them are n's over n's. We're gonna have that kind of a situation, okay? Now, does anybody remember if you were gonna graph this, where you would put the horizontal asymptote? Does anybody remember that? Because that will be the limit. That will be the answer to the question. Where would this horizontal asymptote be if you were going to graph that? What, Annie?
1.
1. You are right. The limit is 1. Annie, how did you know that? No. If this were a 4 and this were a 6, it would still be 1. So Annie has the right answer. That's
I
good.
got you.
Brenton has me. All right, Brenton.
Cancel each other out to 1, right?
What?
N over N.
N over
If
N.
you have the same exponent.
Exactly. When we evaluate limits, we look at the problem and say, okay, where is the highest power in the problem? Well, the highest power in the problem is just n to the first, right? When they match up, and remember, they don't always match up, but when they match up, the answer is just that ratio. The idea is that as n gets really, really big, the 6 and the 4 aren't significant. If I said, Michael, I'm going to give you $1 billion, but I'm going to keep 4 of them myself, $4 myself, you don't care. That 4 is insignificant. These numbers don't matter. N over N is 1. So, what's this one? No. This one would be 2. It's 2n over 1n. Right? What about this one? 4/5. Now, it's all about the biggest power. That's what it's about. So what's the answer to this question? 2/3. It is about the biggest power. We don't care about the other stuff. Uh-oh. This is when the trouble starts, right? What's the biggest power? N cubed. N cubed is the biggest power. How many n cubes are there on the bottom? 0. So I have to write in 0. So my limit is 5 over 0. Well, tell me about 5 over 0. It's undefined. So this one has no limit. If you were graphing this, that would mean it has no horizontal asymptote. The terminology we use in limit land is it's a divergent sequence. That means it shoots off into space. It doesn't have like a ceiling or a floor. It shoots off into space. No limit. Now what about this one? Okay, now Mrs. Ford's getting really tricky. Put a radical in there.
It's just
No, it's not n to the minus 2. What's a square root? N to the 1/2. So on the top here, this is n to the 1/2. This is n to the first. Which one's bigger? N to the first. I don't have any n to the first on top. Remember, it's all about the biggest power. I don't care about anything else. So I've got the biggest power is n, so I've got this now. What's that? 0 over 3. That's 0. That limit is 0. So if you were drawing that, it would have a horizontal asymptote at 0. Okay? So that's one kind of limit problem. And that's a review really, because those were like our horizontal asymptotes. We look at the biggest power in the problem. Alright, so that's kind one. Here comes kind two. Problems like this. And we've kind of already talked about this. Alright, what about these guys? Let's see what's happening here. Alright, let's take a look at these. Now these problems look different, right? The other ones were all ends over ends. These are all something raised to a power.
Did we do this when we were doing exponential functions?
We may have talked a little bit about it. Did we use this notation? I don't remember using the limit notation, but we may have. Exponential functions have an asymptote, remember? Exponential functions look like this, right? So they do have an asymptote, so this limit, we could have had a conversation about that for sure. All right, so here we go. Let's talk about it. What do you think? Now, I want you to just in your head think about letting n get real big. So 1/3 to the 1000th power, 1/3 to the 1,000,000th power. It's 0. It's 0. Isn't that thing getting smaller and smaller and smaller and smaller? Yes. What about this one? Same thing. Because if you let n be 1,000, aren't you raising 2/3 to the 997th power? That's still a really big power. And what happens when you keep multiplying by 2/3, 2/3, 2/3, 2/3, 2/3? Don't you get smaller, 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 smaller? How about that one? Huh? It gets bigger. In other words, there is no limit. That's divergent. There's no limit. What's different about it? Why did these guys get smaller and this guy's getting bigger? The ratio, the fraction here is bigger than 1. That is it. With a problem structured like this, your beady little eyes look at one thing, and that is the size of that number. Okay? If that number is less than 1, your limit's going to be 0 every time. If that number is more than 1, your limit is not going to exist. There isn't going to be one. So let's look at this problem. 0. Now, when you talk about these terms, they do something kind of funny. Negative 1/5 to the first would be negative 1/5. So that would be the first term. But then when you square it, it gets smaller, but it becomes positive. And then you cube it, and it becomes negative, but even smaller yet. So what's happening is, it's flipping back and forth, but every time it flips, it gets closer to 0. So even though it has that flipping motion, the limit is 0. It's getting closer and closer. Every term is getting closer and closer to 0. What about this one? What did Miss Ford tell you? Where do you look? You look at that fraction. I don't care what else is going on. I shouldn't say that. If it's all multiplication like that, that's all that matters, is that number right there. So the limit of this is 0. What about this one? Divergent. No limit. Divergent. Alright, so we've got the n over n type problems that we looked at first. We've got these guys where you're raising something to a power. And then we have one more kind, the easiest kind of all. And we just need it to do our combination problems. I mean, the problems where we put a couple ideas together. There's no n's at all in here. So if I let n be 1, what would that equal? 3. What if I let n be 2? 3. What if I let n be anything? It's 3. Then it doesn't matter what n is, the limit of this is going to be 3. And the limit of this one is going to be 5, and the limit of this one is going to be -7. The limit of a constant is that constant. Okay? So, wait a minute. We're gonna do one combination, or one mix these two ideas together. What would you say about this? What would be the limit of this expression? Now, in calculus, you will study a bunch of theorems about limits, but very simply, you can break this up. The limit of the sum is the sum of the limits. So you can find, to find the limit of the whole thing, you can find the limit of the individual pieces, and then in this case, add them. If that were minus, I'd subtract them, whatever. So what's the limit of this part? 3 plus, what's the limit of that part? Oh, what's the limit of that part?
Oh, I guess 1/4.
1/4. So the answer to the problem would be 3 1/4. You are allowed to find the limit of each piece and then do whatever the operation is. So if that had been a times, it would be 3 times 1/4. Okay? All right, before we take our quiz tomorrow, remind me, someone, that we need to practice, run through page 5. Okay? Before we take our quiz tomorrow, we will run through page 5.
You remember like a little practice quiz that they have actually done that?
Not for this one. I told you exactly what time to get practice quiz. And this one is geometric, but I did last time in zero, so you can watch that one.
I will be here 12 since I've got AP testing.
Wednesday night. Just a minute. Is that off?